A neural network trained on millions of cat photos can identify a cat it's never seen before in milliseconds. A language model reads billions of sentences and then writes like a human. How does a mathematical function learn to recognize patterns it was never explicitly programmed to find? That's what we're unpacking today. Neural networks don't learn like humans memorize facts. They learn by adjusting millions or billions of numerical parameters until input data consistently produces correct outputs. It's a process of iterative refinement, mathematical optimization, and massive scale pattern extraction. Here's how it actually works. First, understand what we mean by patterns. A pattern is any statistical regularity in data. In images, its edges, textures, shapes, and object compositions. In text, its word sequences, grammatical structures, and semantic relationships. In sales data, its seasonal trends and customer behaviors. Neural networks excel at finding these regularities automatically, without being told what to look for. They build hierarchical representations, where early layers detect simple features and deeper layers combine them into complex concepts. A network learning faces might detect edges in layer 1, eye shapes in layer 2, and complete facial structures in layer 3. This hierarchy emerges from training, not human design. The training process starts with random initialization. Every connection between neurons, called a weight, begins as a random number. The network makes terrible predictions at first because it knows nothing. You then feed it labeled examples, images tagged as cat or dog, sentences paired with translations, historical data with known outcomes. For each example, the network makes a prediction, compares it to the correct answer, and calculates an error. The magic happens in backpropagation, the algorithm that taught neural networks to learn. Invented in the 1980s but scaled massively in the 2010s. Backpropagation calculates how much each weight contributed to the error. It traces the error backward through the network, layer by layer, assigning blame proportionally. A weight that strongly pushed toward the wrong answer gets flagged for a bigger adjustment than one that barely mattered. This creates a gradient, a mathematical direction indicating how to change each weight to reduce error. Backpropagation runs on calculus, specifically, the chain rule of derivatives. But you don't need the math to grasp the concept. It's a systematic way to identify which dials to turn and by how much. Once you have gradients, gradient descent takes over. This optimization algorithm adjusts weights in small steps, moving them in the direction that reduces error. Imagine you're in a foggy valley trying to reach the lowest point. You feel the slope under your feet and take a small step downhill. Repeat thousands of times, and you reach a low point. That's gradient descent. The step size, called the learning rate, is critical. Too large and you overshoot. Too small and training takes forever. Modern systems use adaptive learning rates that adjust automatically. After processing one batch of examples, weights update slightly, then another batch, another update. This repeats for thousands or millions of iterations until error drops to an acceptable level. Why do neural networks need millions of examples? Because patterns only emerge from statistical volume. One photo of a cat shows you that specific cat. 1,000 photos reveal what makes cats distinct from dogs. 1,000,000 photos capture cats in every lighting condition, angle, breed, and context. The network isn't memorizing images. It's extracting the essence of catness as a set of numerical parameters. GPT-4, for instance, trained on hundreds of billions of words to learn language patterns at scale. Without that volume, it couldn't generalize to new sentences. This is why data quality and quantity determine AI performance more than architecture in many cases. Overfitting is the failure mode when networks memorize instead of learning. if you train on too few examples or iterate too many times. The network learns noise and peculiarities specific to the training set rather than general patterns. It performs perfectly on training data but fails on new data. Regularization techniques, like dropout, which randomly disables neurons during training, force networks to learn robust features that don't depend on any single pathway. Early stopping, where you halt training before overfitting kicks in, is another common strategy. These methods ensure networks generalize rather than memorize. Modern neural networks operate at staggering scale. GPT-4 reportedly has over 1 trillion parameters. Training it cost an estimated $100 million in compute alone, requiring thousands of GPUs running for months. Image models like DALL-E or Stable Diffusion trained on billions of image-text pairs. Recommendation systems at Netflix or Amazon process petabytes of user behavior data. This scale is why AI capabilities have exploded since 2020. More compute, more data, and better algorithms working in concert. The pattern learning process is identical in principle to smaller networks, but scale unlocks emergent abilities, capabilities that appear suddenly when networks cross size thresholds. Transfer learning is how networks apply learned patterns to new tasks. A network trained to recognize everyday objects has already learned edges, textures, and shapes. Fine-tune it on medical images with just thousands of examples, and it adapts quickly because foundational patterns transfer. This is why foundation models, large networks pre-trained on diverse data, have become the standard approach in 2026. You don't train from scratch anymore. You adapt pre-trained models, saving time and compute while achieving better results. It's pattern learning as a reusable resource. Reinforcement learning adds another dimension. Networks learn patterns from trial and error, not just labeled data. AlphaGo learned winning strategies by playing millions of games against itself, adjusting weights based on wins and losses. ChatGPT's helpfulness comes partly from reinforcement learning with human feedback, where human raters score responses and the model adjusts to maximize approval. The core mechanism, adjust weights based on performance signals, remains the same, but the signal comes from outcomes rather than pre-labeled answers. Here's the bottom line. Neural networks learn patterns by iteratively adjusting billions of parameters through backpropagation and gradient descent, extracting statistical regularities from massive datasets. They don't think or understand in human terms. They optimize mathematical functions to minimize error. But that optimization, at sufficient scale, produces systems that recognize images, generate language, and make predictions with superhuman accuracy in narrow domains. The learning process is mechanistic, not magical, but the results have transformed technology. Understanding this process means understanding the foundation of modern AI. Whether it's the recommendation engine surfacing your next video, the voice assistant parsing your question, or the diagnostic tool analyzing medical scans, the same principles apply. Neural networks are pattern extraction engines. And now you know how they actually work. If this breakdown gave you clarity on how AI learns, subscribe for more no-fluff explainers every week. See you in the next one.